Okay. Then let's start. Where is the mark? So, so we are going to rush through this. So, so pay attention because I'm not. You are not supposed to be learning this at this time or something. So, you guys know what the basic logic gates are: AND gates, OR gate, XOR gates, and you guys know the underlying constructions of those gates, right? What do they use to make those gates? Transistors, right? Then you guys know the operation of a transistor. Oh, then this is going to be fast. So we are going to study. So first of all, I think the entire course is advanced computer architecture. So what we are going to study is that we are going to study some different components of the computer and stuff like that. But basically, the most important, the heart of the computer is what? The processor, the CPU, the microprocessor. So that's what we are going to actually study. And then I know you guys might have done some general stuff on microprocessors and stuff like that. But we are going to pick a particular one, a newer one, not the one developed by Intel and stuff like that. You can't use that one for anything because it's licensed, right? So if you want to design your own CPUs and stuff like that, you need to use one that is not licensed, and then so that you study the ISA, and then you can actually design your own CPU from that. If you use Intel and then you design your own CPU, you might be sued. So we can use that in academia, right? So we are going to study a newer one. It's called the RISC-V CPU. So we are going to study how to construct that RISC-V CPU from the scratch. But the underlying thing is that the first thing, or each each part of that each part of that CPU is made up of logic gates, and logic gates are made up of what? Transistors, I can say. So let's just look at how the transistors operate. So this is the architecture of the RISC-V CPU. You guys know this already. You guys know that within the CPU we have what? We have memory, some small kind of memory. We have register file. You guys know that already. We have ALU, and then we have some kind of control logic and stuff like that, right? So here we have two memories. Have you seen it? One over there and then one over here, right? What type of architecture is this? It's from your computer architecture one. If you have two memories within, how about? And then which one is the other new one? So what is the difference between the Harvard architecture and the new one? So you see how easy that is. Now, which one is better? Why? Why? For two different operations. Probably. What makes it faster? Bus. So you have your probably your CPU. You have memory, right? Memory, right? You have the input output to both the CPU and memory. You have some interconnection here, right? So you said with the von Neumann, there's only one memory, right? So if you want to access data, you must pass through this bus, yes, of course. If you want to access instructions, so within once you write a program, C++, it will get converted to what? Machine code. And then that machine code has some kind of sections. We have data section and then we have instruction section. You guys You guys know that already, right? So we have part will be data, part will be instruction, right? So your CPU reads the instructions, decode it, and then if it needs to use any data, it goes back to read from the memory again. So here, what happens is that you can't read data and read instructions at the same time because it's just one bus, right? But with the other one, you have two. So data is stored in one, instructions is stored in one. So, and then you can read from both. You can read both memories at the same time for instructions and data. Right. So yes, of course, the von Neumann is might be slower a bit, right? But it also has its advantages, right? Now, because for the Harvard architecture, you're using two memories, so your hardware area has increased. You guys know about hardware area. I mean, if you are a hardware engineer, you should know that once you design two of this, your hardware area has increased by two. And then the hardware area leads to the cost of your hardware. The gates within the hardware, once it has increased, it will cost more. So the von Neumann architecture is actually cheaper than the Harvard. Right? Okay, so this is clearly the Harvard architecture of the RISC-V CPU. So each CPU design, like from Intel or wherever, has this architecture. But the difference is that the arrangement within it is what makes it different, right? Okay, so now, how does this code work from the high-level language to the hardware side? How does it work? This is a simple basic C code, right? So how does it work? Let's start from the high level. What happens when you actually write this code and compile it? Yeah. Finish. Into what? Screw didn't get cut. The thing is actually damaged or undamaged based on whether he opens it or not. So, right, continue. Based on what? It doesn't. It doesn't. I don't want. I don't want. Anybody else? How does it work from here to the hardware? So why do you have to write something like this? Because you have your gates here, right, within your laptops or whatever. So why do you have to write something like this? Yeah. Yeah, of course. I mean, you know that for the transistors, right? They only understand 0 and 1, right? So if you are a hardware engineer, all your thinking becomes what? Binary. You're thinking binary, just 0 1 0 1 0 1. That's what the transistors understand. They can't understand what you just wrote. So how do you actually talk to your hardware, right? You need a higher level language, right? Like C, Java, and stuff like that. So this language is just to help you write code that, even though your PC does not understand this, it will have to be what? Converted to a format where which or that it will understand. Right. So you write this, you use this just to aid you write something that you can talk to your hardware Understood? Right. So as you were saying, if we take something like this, like int x is equal to 10, and then you double x and then add 15 to it, and then you store the results back in x. This is a very simple C code, right? So this code will be transformed into the Rex5 assembly language. So we are going to use Rex5. So each CPU from Intel or from wherever have their own assembly language, right? It's just because of how the hardware within their within their CPUs are arranged. You can use Intel for RISC-V, and then you can use RISC-V for Intel, right? So here you use a compiler to actually compile it into the assembly language, and that's the assembly language over there. I think you guys might have seen something like this before, right? So you see that the assembly language matches with the C code if you pay attention to it. Can you see the connection between the assembly code and then the C code? Can we see it? Yes or no? So you see that x is equal to 10. So we are storing some kind of a constant value in a variable called x, or a register called x. Right. So here you can see that we have the first line is add I. In RISC-V, it means add immediate. So you are adding a constant to a value within a register and storing the results back to the register, right? So we have R0, R1, R0, 10. So R0 plus 10 will be added, and then the results will be stored in R5, right? So now, here, the most important is that for X5, the R0 is also so you know that inside your CPU you have register file, right? Each file, each location within that file has a name. So we have for example, we have from R0 to R31, right? So the R0 in RISC-V is stuck at 0. It contains the number 0. You cannot store anything within the R0, but you can store numbers within the others. Understood? So it means that if you do R0 plus 10, it means that it's like 0 plus 10. Understood? So that will be for the first line. So the second line is what? Yeah, you see that it just matches, and then the last line is R5 plus 15 will be stored in. You see that your assembly language matches your C code, right? But here, the assembly language, the CPU don't still understand the assembly language, right? It has to be converted to the machine code before it can understand. And then for the machine code, as I said, it is just made up of what? Zeros and ones, right? And then you might think this is just some kind of random number, 0, 0, 0, 1, 0, 1, right? But each field or each number has a meaning. Can you guess what the meaning is? I mean, I made these slides available long time ago, right? So you guys must have gone through it or not. Have you gone through it before? Nah. But it is still spot or one spot. So okay. So now basically we are going to look at this one later on. Later on, but each field represents something. It could be an instruction, it could be a constant number, it could be a register, right? So now your assembly language or whatever is converted to your machine code, and then it is stored within the instruction memory. So we have two kind of memories: instruction memory and data memory, right? So the instructions are stored within your instruction memory. Then you know the cycle of a CPU, right? You read from the memory, you what? You read from memory, then what? Huh? Debug. I mean, it's just some cycle, the basic operation of a CPU. Read, you have jump. Read what? The code. Then what? Then you write back to memory. Or that one depends on the instruction. So you read decode the instruction. So here you read from instruction memory, you decode it. Is it an addition? Is it subtraction? Is it whatever? Right? Then you execute the instruction. So the instruction could be that add, and then you know that once you're adding two numbers, you have to use what? The ALU. You guys know what the ALU is? The logic unit. So you have to use the ALU, and then after you do that addition, you store back. So you write back to memory or register file. Then you go again, right? You guys know what the PC is? PC, the program counter. You guys know what it does? What does it do? The next program. What do you mean by that? The next instruction? Yeah. So it is also a register, right? That stores the address of the next instructions in line. You guys know this already, so yeah, it's not any. You guys know this already. Okay, so now you know what an ISA is. So here we are just trying to revise on what you guys have done already. You know what an ISA is. What's an ISA? Pardon? What does it do? Hurry up, hurry up, hurry up. ISA. What does it do? Like, what is it for? It does what? Where do you use the ISA? You guys know this already. Don't disgrace your lectures. Like, I mean, it's just simply the language of the CPU, right? And then that's what you use. So for you to design any CPU at all, without knowing the ISA of the CPU, it's impossible. So you have to look at the ISA of the CPU, and then you can use that ISA to actually design that CPU, right? So it's just the language of the CPU. Understood? Now this is just the computing, basic computing system. Like you guys know this already. You know that we have three components within any kind of system, a computer system. It could be a laptop, a desktop, your probably your phones, your embedded system, whatever. Right? You have the computation unit, right? You have the communication unit, and then you have the storage unit or the memory. What's the difference between memory and storage? Like from here. Yeah. It's as simple as that. Okay, so now you guys know that we have the memory processor. We have a bus that connects the memory to the processor, right? This is a typical von Neumann architecture, right? We have combined instructions and memory. Then you read from memory, and then you guys know that there are different types of buses, right? And then for the bus, so how, as I said, you have memory, right? You have memory, and then this memory stores both data and instructions. So how will you know that you are reading from an instruction place, or you're reading from a data kind of portion of the memory? How will you know? Pardon? It's connected to the instruction part. Can you see just one line there? So how does it connect to the instruction part? How does it request it? Because you see, what it does is that if you want to read from memory, the basic thing is you have your memory here. This is how memory is arranged, right? So you have your data weight here. Data weight. You guys know this, right? So it could be 8 bits or whatever. And then you have your depth, right? The depth indicates the number of locations within the memory. And then you have your memory addresses, so probably 0, 1, 2, 3, 4, 5, 6. Right, so you can use this information to actually calculate the size of the memory in bytes, megabytes, or whatever. Right? You guys can do that, right? If I give you data with and then the depth and then whatever, you can calculate the size of the memory. Okay, but I mean that's not. So this is how it's arranged. And then your data is stored here. Right? So now you have only one connection here to the CPU. Right? Now, on this line, you can request for information. And then to request for information or to request for some data from the memory, you need to give it an address because it needs to know where, right? So maybe I want to read from this location. I have to give it an address, right? And then the data will be read to the CPU. If I want to write it to it the same way, I give it an address and I give it data from the CPU, and then it will write to it. Understood? But here, the issue is that uh, you have instructions being stored in this CPU, right? You have data being stored in this CPU, right? So how will you know that this is instruction and this is data? Yeah.
You store small information with writing whether this is an instruction or this is the
You store some money where? Where do you store that?
we are alongside with the register.
There's no logic inside here anymore. It's just memory. All it does is that it has ports for address and data. Once it sees this address, it gives the data from that address to the CPU. That's all it does. So how will the CPU know that this is instructions or this is address?
Unless maybe you have to assign some of the space inside the memory for data, some of the space inside for instruction. When
Yeah.
it goes to that, you know that this is
Yeah,
data.
exactly. So what you do is that you do what is known as you have an address space. So you have address space. Let's say this is 6, right? So now from the onset, once you write your code at high level, right? Once the code is actually being compiled to machine code, right? It will indicate that from address 0 to 3 is for instructions. So instructions are stored there. And then from address 4 to 5 stores data. See, simple stuff like this is what is going to come in your exam. So as easy as that, right? Should I continue? Any question? Yep. Yes. Yeah, every kind of CP does that.
Since we have the urban architecture, we have different memory for data and different memory for
Yeah.
instruction. So then once it is going to this memory, it knows that it's definitely going to be
Hold
data.
on. For the Harvard and then the von Neumann, you the you have a choice, right? If you get an if you get an ISA of a CPU, now you will now choose whether to implement it as Harvard or von Neumann. So that one, it doesn't matter. All of them can use Harvard. All of them can use von Neumann. It's not an issue.
So they're responding.
I mean, it can be Harvard, it can be von Neumann, so it doesn't. But yeah, shall I continue? Any question? Okay, so this course is like, okay, you know that within the computer system, you have your application, your software application, and then your lowest level is the what? The circuit itself, right? The electrons and holes. So you guys have done semiconductors. So electrons and holes and how they move and stuff like that. You guys know that, right? So on top is the application, down is the electrons and hole, and then we have some abstractions in between them, right? So it means that here, what we are going to be studying is the ISA mostly, and then we are going to also study the micro architecture of the ISA, and then we are going to study some basic logic gates, the logic gates to use to design the micro architecture of the ISA, right? We are not going to go below the devices level. The devices level are the transistors, but you just have to know how they work, just simply. But that is another course, like semiconductors. And then you are not going to go above the ISA. The ISA is for software engineers, so like learning how to design a software application. So we are going to be stuck within the ISA, the micro architecture, and then the logic gates. Understood? So you guys know that, or you guys have seen this image before. This is the first transistor the first transistor that was made. I hope you guys know that. But you guys have done you guys did semiconductors, and you didn't see this. Okay, so this is the first transistor that was made, and then it was made in AT&T Bell's lab in 1947, right? And you guys know the operation of a transistor. How does it operate?
Like a switch, smart switch.
And so I shouldn't even be teaching some of this. Did you guys know them already? I'm just wasting my time, right? So basically, uh, computers are made up of transistors, right? And then, as you saw, this is the first transistor, right? Now, each year, when you go to probably in 1971, right? Intel made the Intel 4004 transistor, right? This, uh, they made a CPU, 4004 CPU, right? This one had about 2300 transistors, right? Those are the number of transistors within that CPU. Now, in 2000, right, Intel made a Pentium 4, right, and then the Pentium 4 contains 42 million transistors. So you see, there's a jump, right, from 2300 to what, 42, right? Now, in 2022, if you look at the Apple M2 Max, right, it's made up of 67 billion transistors, right? So now you know that devices probably from Intel 4004 to the Apple, you know that the devices are shrinking, right? The device itself is getting smaller and smaller. So how are they able to do this? How are they able to scale to the point that they're making the device itself smaller, but they are packing a lot of transistors within them? How is it possible? Pardon? You guys studied semiconductors, so this is not supposed to be an issue at all. Pardon? What? I can't hear. Has done what?
Asking more devices inside micro devices.
It has done what? Like,
So the same way you can pack micro, micro, in one, there's something small, but it contains huge amount.
What I mean is, how are they doing it? Okay, that will be one question. So you guys know what the MOS transistor is? Metal oxide semiconductor. You guys have done this already. So we have the MOS transistor. That was the first transistor that was actually made, right? It has the source, the gate, then what? The drain. This not. So here, this is the architecture or the symbol, let me put it that way, of the MOS transistor. You guys know what this is? The N type and the what? P-type. We are not going to go into details, but and then you know how you know how they operate, right? Okay. So they just operate like what you said, a switch. You turn it on and then your light comes on, and then you turn it off and then your light goes off. And then you know that the N type is made up of what? Electrons. The P type is made up of holes. Simple as that, right? Any question? So now the basic thing is this is the N type, right? So it is made up of electrons, right? So how does this N type work? Anybody? Yeah. By passing what? High voltage. What do you mean by high voltage?
So it depends on the system.
Okay.
The system will determine there's a range of
Yeah.
voltage that if the voltage is in that range, you can say it's a high
Okay. So in electronics, what is the highest? What voltage can you supply to it, or what voltage do you think is a high voltage? 0.3 to 3.
voltage. But anything above 1 volts,
It's, it's high voltage. Okay, fine. But okay, so this is the gate, right? So you apply probably drain source. So you apply voltage here, and then applying voltage means that some use 5 volts, some use 3 volts. Right. Now, if you see 5 volts and 3 volts in data system, it just means logic what? Logic what? One, right? If we see 0 volts, it means what logic? Zero. So you apply, so anytime I say apply voltage, I mean 5 volts or 3 volts, depending on the system. And then you must know that 5 volts or 0 volts just means logic one or on. And then 0 volts means logic zero or what? Off. Or true or false. Right? So just binary. Right? So now you apply voltage here. And then this voltage, so if I apply 0 volts here, what happens? Higher. You guys have done this already.
So when you apply 0 to the end, like, it's off.
It's not the N type. I've applied 0 to the gate of the N type here. What happens?
Said the channel is closed. The channel that the gate is closed.
And then what? Huh?
It doesn't allow flow of electrons.
Okay.
There's no
Okay.
electrons flowing from the source to the drain.
Yes. I mean, that's true. So you can just envision this like some kind of channel, right? So if I apply 0 volts, like just like your switch, it's off. So there's no flow of what? Electrons. Or there's no flow of current. Somebody will say flow of voltage, but you guys know voltage won't flow, right? Engineers. Okay, you know that there's a flow of current or whatever from the source to the drain. So if you So if I apply 0 volts here, and then the source has 5 volts, right? The output will be 5 volts. There's not. So here is closed, right? So it will be 0 volts. Understood? Okay. And then you know that the other one, the p-type work opposite of the. We know that, right?
Yes, sir.
There's a circle here. So even there's a circle here. So if I apply a 0 volt, what happens?
It will come on.
It will close the the gate and it will allow the flow of current from the source to the drain. So if the source is connected to 5 volts, it will be 5 volts. If it's 0 volts, stuff like that. So now you know this architecture, right? So now how do you use these gates, this transistor to construct the logic gates? These architectures are the basic construction blocks of any digital system. The next abstraction is the logic gates, right? So how do you use this to construct logic gates?
So since they are booleans, like 0 1 0 1, it's a combination of
Yeah, yeah, yes, yes, yes,
those cases.
yes. So now at first, right? I think probably in the 70s and 80s or so, they were using only the they were using only the NMOS to construct our circuits because it was difficult to handle the holes. The holes handling was very difficult, but now they've been able to handle holes and electrons easily, right? So now they use what is known as they combine both the NMOS and PMOS to construct your circuit of your complete system. So we call that CMOS, complementary metal oxide semiconductor. This is the combination of the NMOS and then the PMOS. Understood. So we use the CMOS so you can combine several of them, NMOS here, PMOS here, to construct your basic logic gates like the AND gates, OR gates, NAND gates, and then basic stuff like that. So what is this gate called? So here you see that I've combined the NMOS. Have you seen the down there? The NMOS is down, the PMOS is what? Up. Right? And what is this gate?
Yes, and
So it's a sequence.
Oh, master.
it's a not
So how can you know that it's a NOT gate?
it has input of one or on, and it comes out as 0.
So the input is inverted, whatever you give it is inverted.
So okay, so now let's go through it just simply, right? If I apply 0 volts to the in, what happens?
0 volt, the first one will be on, the second one will be off. I mean, the one at the top will be on, that's the P type will be, since it's 0 to be on, and the second one will
Maybe
be
off.
off. So there will still be a shortage of flow of current somewhere. So it come off.
Somewhere where? That is the circuit. You have seen the circuit over there. So
Put very good.
what is put there?
The input signal you apply.
Engineer, so you guys must know how to analyze circuits like this. So how does it work? If I apply 0 volts to in, and I mean we're on the right path, the top is on, right? So the PMOS is turned on, but the NMOS is turned off, right? And then you see that on top you have a 3 volts there. Now when you see a circuit like this, what you're looking for is the input and output. If I apply voltage to the input, what happens to the output? Right. So now what happens to out if the PMOS is on? You see that on top there's a 3 volts, right? So the 3 volts, the current will flow until you know that the voltage there must be some kind of potential difference. So the 3 volts will have to appear at the output. Do you understand? So if I apply 1 volt to the input, what happens?
It comes out as
Master, let's always go through the circuit. We are going through the circuit. So what is on, what is off?
So then that one will be on the top of zero will pass through.
Can can zero pass through it? I mean, it doesn't pass through it.
So zero comes out.
Yeah, yeah. But the most important thing is that, so let's say you have a circuit like this, right? You have your output to be like 3 volts already. Now, if you apply a 1 volt over there, right? So you see that you have connect. Once you say this is ground, you've grounded your. So if there is any kind of voltage at the output, it will drain and then the output becomes zero, right? So if you apply a 1 here, the output is what? If you apply a 0, the output is what? And then that's a what? Or an inverter. Are we all on the same page? I assume that you guys know this already. That's why I'm going too fast. Huh? Are we all on the same page? Do you understand? Do you understand? So we are all on the same page. I mean, some people are actually answering the question, so that's why I assume all of you understand. Okay, fine. I mean, the exam will actually determine who understands and also. What is this gate? So now we know the NOT gate, right? You have seen the inverter, right? What is this gate? So we have 2 inputs. So anytime you see something like this, right? What do? You take your inputs A, B, right? And then we have one output, Y, or out. Once you have 2 inputs, you know that you are going to be applying 0, 0, 0, 1, 1, 0, 1, 1. Something like this, right?
Yes, sir.
So now you first of all have to take the first case, 0, 0, and pass it through the circuit. So A is 0, B is 0. What is on, what is off? Just trace this. Hurry up, hurry up, hurry up, hurry up. So B1 is what? P1 on. So it means that below the down is off. The top is what? On. And then what happens to the output? So it's on means what value is it? 1. Simple. So 0, 1. If A is 0, B is 1, what happens? Hmm? How will all of them win? No, no, no. Go through. Hurry up, hurry up. Hmm? B1. Yeah, and P2 will be what? And then. Uh-huh. So what happens to the output?
Since it's parallel, we need one top.
Nasa, hurry up and give me the answer. I
The
don't.
top will be on. The top will be on. The top will be on.
The top is P1, P2.
So
P1, P2 are all on.
no, one is on, one is off. But the resulting billing is that it will be on the top side will be on.
And once the top side is on, what happens? You see that it's parallel, right? So what? One is on, one is off, but they are in parallel. You know, circuits in parallel. What? 1 0 1 0. Was this 1 or 0? 0 0 was what? 1 0 1 0. 1 1 1. What?
Both the N1 and
Yeah.
N2 and P2
Off. Simple.
ground.
0. What gate is this?
So what is
Ah.
none?
What gate is it?
The none.
Yeah. This is a NAND gate. Not and. Because an AND gate, it will be what? And once you invert that, it becomes a NAND. Easy, right?
So can you call this a decoder? Not at all.
Okay. It's a NAND or AND gate. We are not at decoder level. I hope you guys understand. From the back, you guys understand, right? It seems only the front guys are answering. And after that, they all get 5 marks, and then all those at the back guys. That's fine, right? Yeah. So now you'll be fighting for 95. And then each day it will reduce. That's still fine. Okay, so we know that this is a symbol for the NAND gate, right? You guys have seen it before. Just a note at the, and then it just means that the inputs are inverted. Okay. So this is a truth table of an AND. So if if this is a NAND gate and I want to convert it to an AND gate, what do? I just convert an inverter like this to the output. And then we have an AND gate, as easy as that, right? So now you see that you have a NAND gate, you have an AND gate. Now you must pay attention to the number of transistors within each gate. Right? The NAND has how many transistors? The one we just saw, 4. The AND has how many transistors? 5. So 6, right? 6. So now when you are designing in hardware, actually, not at high level language, like if you are a hardware engineer, and if I say hardware engineer, I don't mean you actually repair pieces or something like that. But if you are if you are coding to actually design a chip, right? You use very, very low level language, not assembly language, but very low level language. You guys have heard of VHDL before, right? You've heard of Verilog before. Now, once you are coding, right, you must be careful about the number of gates. As I said, the number of gates within the chip translates to the price of your hardware. So if you are a designer and then you are designing your chip and then you are using more of AND gates, you see that your chip price will be increased based on because it is using more gates. But if you are using NAND gates, you see that the price of your chip will actually reduce, right? So that is what will make a good hardware engineer or a bad hardware engineer, right? So once you get employed in places like where's it? Like Samsung. Okay. Yeah, then yeah, Qualcomm. Samsung, Qualcomm, um, LG, and places like that, right? They base your work based on the number of gates that your code actually produces, and then they pay you based on those kind of stuff, right? So if you go further to study for masters and PhD, and then you actually choose a hardware engineer, you actually choose to be a hardware engineer. That's what they're going to judge you on, based on how many gates your gate or your code will produce, and then they'll know whether you're a good engineer or a very, very bad one. Because if you're a bad one, you cost them more money. If you're a good one, you cost them less money. Understood? Okay, so now we have seen the NOT gate, we have seen the NAND gate, we have seen the AND gate, and then we know the architectures already and stuff like that. You guys know what the Moore's law is? What does it say?
The number of transistors multiplied by
Every 18 months, right? You guys know this already, so these are just basic stuff, right? So Moore's in 1965, right? He envisioned that the number of transistors within the logic gate, within a digital system, right? Within the digital system will actually double every 18 months or almost every 2 years, right? And he has been right for some time, right? If you check the trend from probably 1970 to about 2005, right? He has been right. Every 2 years or every 18 months, the number of transistors within a digital system actually doubles. But I think it has slowed down from 2005. It has become kind of linear, so it has become stable. Right? Why do you think that is? The number of transistors are not being able to double anymore within a single chip.
maybe the area, hardware area, or we are not using their parts yet.
Or they are very, very bad.
Maybe. Anybody else? Why do you think that the number of transistors within a single chip cannot be doubled anymore? Why? I mean, if anybody can answer, just free 10 marks for you. Yes.
Double is the extent that the space between the two transistors have become very small. So if you push it together, it will overlap.
What's that? You were going the right direction, and I thought you were going there, but yeah, like, the deviation was just.
So I think that they are giving us that for portable hardware.
No, master. Anybody else? Just free 10 marks. Just so now you just be fighting for 90%, 90 marks. That's all you are done. Eh? Cannot do it. Oh, master, you should do what? Why are you dissing the hardware engineers like that? Pardon? Oh. Anybody else? Just the last person, then the 10 marks goes away. Huh? Hurry up, hurry up, hurry up. I mean, if it has been packed, so what? So what? No. The way you are laughing is that. Oh, yes, they are what? I mean, that is the goal. So. What? Due to what? Source. You have seen this. You have just actually Googled it, right? Okay. Now explain. Yeah. Oh, please keep quiet. So yeah, that is actually correct. It's correct, but now explain because it's just a term you are just giving. Source train leakage. So explain. Huh? Pardon? I can't hear you. Ex- Explain it in your local language. Yeah. Yeah, so that is one. Yeah.
So the goal is to make the chip so small.
Yes, of course.
And we are also trying to pack as many as.
Yes, of course.
So the more you are packing and the chip becomes smaller, eating issues and other things.
That is the other way. So 10 marks for you. Then I think one more question. Uh-huh. Don't use terms that that you can. Please what? Super. Yeah, that's what he said. Yeah. So you share the marks. So the first thing is that in if you study the semiconductors, this portion is what is called the channel, right? So now what they are doing is that they are shrinking the sizes of the transistors, right? And then all they are doing is once you want to shrink something like this, they have shrunk this to a level, the top to a level, right? Now all they are doing is shrinking the channel, right? They are making the channel smaller every year. That's what they are doing, like in the past. So they've made it smaller to the point that you know that once you make it smaller, the source is connected to a voltage source, and then current flows from here to here, right? Once you make it smaller, and then without it being on or off, without the gate being on or off, there will be leakage current. That's what he said at first. So there's a source drain leakage kind of current once we made it smaller. So they can go beyond some kind of level. If not, there will always be leakage current from the source to the drain. So that's one reason. Right? Another reason is that they are packing them so much, and you know that these transistors, once they are on, it produces heat. They can't handle the heat. They are not able to handle the heat that are being produced by a packed number of transistors. So now they are stuck. Understood? So those are the two reasons. Yep.
Is that also why they are trying to explore the quantum computing?
The what?
And is that the reason why they are trying to explore quantum computing?
I mean, quantum is they're using different kind of materials instead of the normal transistors. Oh yeah. But they were doing that a long time ago before this issue.
So does it mean if they take care of the eating issues, there's still the leakage that they have to take
Yeah, they have to take care of. So there are two main issues that they are finding it difficult to. So now they are just stuck between what they have now. But they are still advancing. There are still analog engineers out there who are still exploring how to. And then they are now exploring how to use different materials instead of the semiconductors and stuff like that. Go and tell them if you go and do your masters, you can explore. If you go and do your masters or PhD, you can explore that. Yeah, you do it. Okay, that's all for this slide. There are 5 more to go.